National Institute of Standards and Technology. And although he recently retired from NIST, fortunately he was still working there when my former student, Regina Easley, began working there under his tutelage for a number of years. In projects started at NIST under Ken's direction, procedures are now being developed by Regina and also Jason Waters, a student of Dr. Frank Malero, for enhancing the accuracy of spectrophotometric seawater pH measurements. Dr. Pratt received his PhD from Iowa State University, and prior to that, dual degrees in chemistry and Russian from Lafayette College in Pennsylvania. Ken's CV documents his work on an impressively large number of standard reference material projects and extensive work with the International Union of Pure and Applied Chemistry, where he was recognized as an IUPAC Fellow. Late last year, Ken gave a presentation at Ekaterinburg in Russia that incorporated some proportion of what you'll see in today's presentation. And Ken generously sent me previews of today's talk as he was preparing it, serially, updates about every day or two. The first PowerPoint version was almost entirely in Cyrillic. As time has gone on, his updates have contained greater and greater proportions of English. It would be too bad if all of the Cyrillic has been eliminated, because some of his former presentation apparently contained jokes that only work well in Russian. The title of Ken's talk today is Production and Traceability of NIST Electrochemical Standard Reference Materials. Ken?
Большое спасибо вам, Dr. Bern. It's giving me great pleasure to be here to present talk on production and traceability of electrochemical and spectrochemical standard substances. Standard substances called SRMs at NIST. It's great pleasure to be here in St. Petersburg. No, it's St. Petersburg, Florida. Okay, I can do this in English. Okay. Das geht ein bisschen besser, ne? A little better in English. That was German, not Russian. I speak much better German than I do Russian. Anyway, production and traceability of NIST electrochemical and spectrometric SRMs at NIST, University of South Florida, the same as what you saw before. When Bob, I'll say Bob for Dr. Byrne, when Bob first invited me here, I agreed, and in the interim I wound up, I'm selling a house. I have boxes full of books in Gaithersburg and boxes full of books in Rockville, which is only 10 kilometers away, but still, I don't know what box the books are in. And then Bob says, please tell me the title of your talk so that we can publicize it. I say, talk? The only thing I can do is translate the talk that I gave in Yekaterinburg last October. So that's what I did here, and that's what you got. And I added some things that are of specific oceanographic interest here. Does this thing turn on? Does this turn on? Do I have to turn it on here?
Oh, it does turn on.
It's okay?
Yeah.
Okay. So when I started the talk in Yekaterinburg, when I was a student, this is an old picture of me from 1973. I obtained a Soviet visa from the Soviet Embassy in Washington, valid from the 3rd to the 24th of August, 1973. And went, the group flew from the United States through Kennedy Airport, which had just been renamed at that point from Idlewild, which it was before Kennedy was assassinated, to Helsinki, and then flew to, at that point was Leningrad, and then went to Kiev and Sochi and Kharkov, which is not on the visa, and to Moscow, and then went back. I had been working in Germany, in Mainz, in Germany in the summer. I took the train from Mainz across East Germany, across Poland, across a little corner of the Belarusian SSR, which is now Belarus, and across Lithuania, had to change trains at Vilnius, the capital of Lithuania, across Latvia in the night, and wound up in Leningrad, which is now, again, what Peter the Great named it, St. Petersburg, which is the namesake, what gave the name to St. Petersburg, Florida. And there's Leningrad there. This is what a Russian visa looked like back then. And after that, I never went back to the Soviet Union, but times changed. This is 1973. In 2000, since 2010-11, I got to know people at UNIM, particularly Alena Sobina, who does coulometry at UNIM in Yekaterinburg, and she had many times invited me to go to UNIM. And we know each other from working where in France we meet, all the national metrology institutes, I'll talk about that later, meet, and we have these international comparisons, and we all compare how well we can make a given measurement. And she had invited me a number of times to go there. She knows I speak Russian, and when I first met her, I started speaking Russian with her. And her English was not so good, so it was kind of a positive outcome. But then at Yekaterinburg, I addressed specifically the director and said, many thanks for the invitation to the visit to UNIM. That's a picture of the UNIM building in Yekaterinburg. This is the official invitation which you need to get the Russian visa, invitation number with the number blocked out for the entry into the Russian Federation, which is issued by the secret police, the security organs. And UNIM had to issue to the police in Yekaterinburg, they had to issue a letter of invitation, whereupon a month later they issued this to me, and it turned out that Alena Sobina was coming to West Virginia to do business travel there, and she got, well, would she get the United States visa? That was another question. And she wound up going to near White Sulphur Springs, West Virginia. I took the train down from Washington down to White Sulphur Springs. She gave me this paper, and I took it down to a Russian embassy in Washington, which is like Kremlin with high wall around it and is very high up so they can look down and intercept all the United States governmental communications. If you've been in Washington, it's on almost the highest point in Washington, overlooking all the government buildings in the valley. But with respect to the present talk, well, no, excuse me, this is, you saw this slide here. This is me in Yekaterinburg. Alena took the picture of me here talking back in October on this same slide here. But with respect to the St. Petersburg talk, many thanks to Bob Byrne for the visit to not UNIM, but USF, College of Marine Science in St. Petersburg, Florida. What are we going to talk about? The main stress is what I worked in for many years, which is categories of electrochemical SRMs. And to give background on that, what are the steps in the certification, not only of electrochemical, but all standard reference materials? To understand what the steps are for the electrochemical ones, you need to know the primary electrochemical measurement methods that are used, calculation of uncertainties. You kind of have a feel for what I'll give the definition, the official definition in a minute. Traceability, again, I will give the definition of that, of the certified value. The standard reference material has some measured property, and it has a certificate that gives you the certified value and the uncertainty on that value. How well do you know it? You'll see that a little bit later. And then that's the electrochemical part. I put in, because of specific interest for UNIM, because they do a lot of inorganic elemental measurements, NIST has a large program in spectrometric standard solutions. Standard solutions, the SRM 31, XX 3101, 02, 03, etc. I will talk a little bit about that. Then I will talk, this was not in the talk at UNIM, but is of interest here with Bob Byrne's group, development of a NIST metacresol purple, MCP, reference material for traceable seawater pH measurements. And then if we have time, I may talk about a joke, which this is one, he who laughs last is the one who has to have the joke explained to them, and that may apply to you here, but it didn't apply in Russia. They understood it. So first, some metrology speak for non-metrologists, not meteorologists. Meteorologists do weather forecasting. Metrology is the science of measurement. So meteorologists do metrology in that they make temperature measurements, they make pressure measurements, they make humidity measurements. All of those, you need to have a value that you measure and an uncertainty, if you will. But the only interest that metrologists have in meteorology is it going to snow? Can I get to work on time or something like that? Or a hobby interest or something. But generally, this is the science of measurement, and there is an international protocol defining all the vocabulary which is used. It's called Vocabulaire International de Métrologie, and with a lot of the diplomatic languages there are parallel in French and in English, and the French is, in Germany you say maßgebend, or is the governing version is the French version. The English is there for information only, if you will. But everybody uses it in English because all the meetings are in English. International Vocabulary of Metrology. If you want to use the words correctly, you can go online and read it, and it makes for highly fascinating reading. Taken from that are the definitions of what I will be talking about: traceability, the property of a measurement result, whereby the result can be related to a reference, a standard, through a documented, unbroken chain of calibrations, each contributing to the measurement uncertainty. So what's the measurement uncertainty? Measurement uncertainty is a parameter that characterizes the dispersion, the scatter of the quantity values, the measured values, being attributed to a measurand. A measurand is the quantity being measured. This is all metrology speaking. Measurand, you've never heard that word before. It's a word. Another useful source, which you can get from the same link as on the previous slide, Guide to the Expression of Uncertainty in Measurement. I call it Goom. You see that, you probably think gum like chewing. But when I see Goom, I think Glavny Universalny Magazine, which is the main department store in Red Square opposite where Lenin's tomb are and where the Kremlin is. So I always call it Goom. This is, I guess you can download, this is the first page of it. Evaluation, title has changed a little bit. Evaluation of measurement data, Guide to the Expression of Uncertainty in Measurement. And of course the French is governing. Interestingly, if you read Russian, metro chru, but it looks like almost metro chru, and chru is the sound of pig and oink. So it sounds like metrology is oink oink, which looks a little funny. This is Goom in Moscow. This is what, when I talk about people talking about the Goom, I think of this building. Lenin's tomb is back over here. This is Red Square. And this is the Goom building here in the daytime. This is at night. And inside, you see the main store on, on Red Square. Goom on the, 1893, Red Square. There's Goom in Latin letters. It's like a giant airport duty-free store with all these fancy brands because it's, Russia has changed. It's not the way it used to be. Not the main store, but the governmental store, the federal governmental store, Государственный, now it's Glavny Magazine. So the title changed with the changes in the former Soviet Union. What is a standard reference material? By the way, the SRM, this is actually legally a registered trademark. National Bureau of Standards is what NIST was before 1989. And NIST issued, NBS and then NIST issued and still issues standard reference materials. They're protected by a trademark. Internationally, these buttons are too close together. Internationally, these reference materials that have a certified value and uncertainty are called certified reference materials, CRM. The ones produced by NIST are standard reference materials called SRMs. NIST maintains with a degree of truth that the SRMs fulfill all requirements of CRMs set forth in the International Standards Organization. That's another one of these international bodies that gives guidelines and protocols for international recognition of all kinds of scientific and technical information. Guides 34 and 35 specify how you are to certify a certified reference material. But the NIST SRMs, there is additional measurements for determining long-term stability, like 20 years down the road, how close is the measured value to what you had 20 years ago. And the NIST quality management system, which says, yes, the staff that are making the measurements are qualified to make the measurements. When we make the measurements, you say what you do in official reports that are signed off by the appropriate management. And these reports and all supporting documentation and calibrations are stored as dictated in these guides. And people say, oh no, not again. But that's a big thing in metrology institutes now. This is one example of an SRM certificate for the borax sodium tetraboric decahydrate. It's the pH standard, pH about 9.2 at 25 degrees Celsius. And this says what it's for, the certified values. If you go to the second page, often the certified value is on the first page. For this one, the certified pH is temperature dependent. So you see a whole series of temperatures, the respective pH values, and then you have what they call combined standard uncertainty here, what they call the coverage factor. This is like one standard deviation, but it isn't only the scatter, it's the scatter to which you have a combination and quadrature of all the other sources of uncertainty that enter into the equation that gives you the pH. And then this is what they call the expanded uncertainty here. And all of this is specified, this is defined, you see here. And the combined uncertainty for the measurement, it's confusing for pH because there is a convention that enters in here, which is most of this. Most of this source here is derived from the uncertainty of this reference, which is the uncertainty of the uncertainty of the convention, excuse me. That uncertainty has been agreed upon by a commission in IUPAC, International Union of Pure and Applied Chemistry, that had a recommendation issued in 2002. Many other SRMs don't have that issue, but because of how to get to single ion activity, you've got to get a convention to get from mean activity to single ion activity. What are the electrochemical category SRMs? pH buffer solutions, of which you just saw a representative certificates. The 2002 recommendations from IUPAC specified tetroxylate really as a secondary, but the primary ones, phthalate, phosphate, 2 formulations, borate, which you just saw, carbonate. Calcium hydroxide is kind of a secondary one because it isn't a direct solid substance that you dissolve. It's issued as calcium carbonate. You have to ignite it to calcium oxide, add water. It makes a lot of heat, and calcium hydroxide, you then make a saturated solution. It's about pH 12.5 at 25 degrees. It's used in cement. Cement pH values are very high, so you need a standard up at the high end of the pH range. A lot of the electrochemical SRMs are what we call primary substances, benchmark substances for titrations, titrimetry. So redox SRMs like potassium dichromate, a number of acidometric ones, potassium hydrogen phthalate, which is the biggest, the largest selling SRM, single SRM at NIST, sodium chloride, potassium chloride, sodium carbonate for acid base, a weak base, tris hydroxymethylamino-methane, boric acid used in acidometry, and there are some others too. These are certified using coulometry, which you'll see in a little bit. Essentially is an electrical titration where you're generating the titrant by flow of electrical current rather than taking a titrant out of a bottle. The nice thing about that is it's absolute, governed by what are called Faraday's laws of electrolysis. There is one SRM, and there may be more in the future, that are not determined directly by coulometry, but you indirectly titrate this against a substance which you can then standardize using coulometry. The example of that is sodium oxalate. That is an oxidation reduction standard particularly used for the standardization of potassium permanganate solutions. And then electrolytic conductivity, ionic conductivity in solution. Essentially, they're dilute solutions of potassium chloride, mostly in water. There's one which is a very dilute solution of hydrochloric acid in water. And right now they're out of stock. That's another story. Don't ask me about that. For any SRMs, not only the electrochemical ones, you go through a general series of steps. You have to get the material. Before you get the material, you have to put in, by the quality system, You have to get approved by management. What is the certification process going to be? How do I get the material? How much is it going to cost? How much time? The scheduling time and dollars and facilities, but also what subsample of the entire batch are we going to use? Statistical analysis has to come in. You have to plan this before you buy the material. How many bottles do you need? How much demand is there for the material? You have to plan this all in advance. Once that's approved, you can go ahead and purchase the material. Normally, NIST does not make SRM substances directly. They are purchased as reagent-grade substances from outside manufacturers. NIST does not have facilities for making, like for potassium hydrogen phthalate, a 780 kilogram batch of primary standard grade potassium hydrogen phthalate. No way does NIST have the possibility to do that. Then when we get the material, it's a candidate material. We have to accept it. Is the material of sufficient quality, homogeneity? Are all portions of the batch close enough to the value that we expect to see for the material? Is the scatter small enough that it is acceptable for issuing an SRM? Remember, these SRMs are used by manufacturers to calibrate not to calibrate, but to test for the quality of their product. So the SRM has to be a better quality than what the manufacturers make. Because remember, each step in a traceability chain, the uncertainty gets larger and larger. So if you have a larger uncertainty on the calibrant that the manufacturers are using, how can they make a better product? They're limited by what the SRM would be. Then when we accept it, then it goes to the SRM division, who packages the lot for it can be a very large number. Typically there are bottles of between 20, say, and 100 grams, normally about 30 to 60 grams. 30 grams typically for the pH SRMs. For the titrometric, the coulometric SRMs, they're usually between 20 and 60 grams. The conductivity SRMs are issued as liquids, so that's a little bit different. Liquids have a problem. They are not stable. Mold grows. Things grow in liquids. Bottles leak. You take a bottle and put it in an aircraft at altitude, the pressure in the hold is 3/4 of an atmosphere. That means you have 1/4 of an atmosphere pressing outwards on the seal. If the seal is not watertight, you get drops of liquid. Drops of liquid that may be acidic or something. Oh, it's a chemical. All the passengers are going to die. So then you call out the police and it gets to be a big thing in an international shipment. We've had that problem. These things happen. And people get in trouble and heads roll.